so much for joining us. We'll get started shortly. As a reminder, with all of our S.T.A.R forum events, please do engage us using the Q&A module. Audio as well as video and chat are unavailable during the event itself, but we do make sure to follow up on all Q&A. And then after the event, if you submit the very brief survey, share your feedback, and if you want to reach out to us, we will absolutely engage with you at that point as well. So we are so excited to get chatting with you today. I'm just going to give it another couple of seconds. Let's see if we can get some interactions. If you can see the slides on the screen, if that is visible to you, if you can give me a thumbs up. Wonderful. All right, we're already rocking and rolling. Love it. Okay, we're going to start kicking us off. I'm going to bring my fearless co-host on screen as well, Samantha Gardner. Love it. Okay. All right, we are here for episode 7 of the Defender Experts S.T.A.R Forum. We have a jam-packed agenda to dive into. We have a couple of heavy hitters from our Microsoft security team here with us. Really exciting content. We're going to grant the stage to them, and they're going to take us through all of their research, all of their perspectives, recommendations, specifically around cloud and AI compromise in kind of a non-traditional way. As I mentioned previously, if you're just joining us for the first time, chat, audio and video are unavailable during the event itself, but please leverage the Q&A module within the webinar. We will absolutely follow up with you. And then after the event itself, if you go ahead and submit the very brief survey after the session, we will follow up and we can have more focused conversations at that point if you are interested. So with that, Sam, I want to let you have the floor. Is there anything that we have to cover before we hand it off to Dewas and Avi?
I will sit here and say, everyone, take notes. If you have questions, you can put it in the QA. We are very much monitoring and staying on top of it. So please ask all the questions that you want. This is your opportunity to talk to the expert, right? And get that first line knowledge about how to pivot in our telemetry, what to look for, especially with this new hot topic with AI. What does AI look like, and handling cloud, which is something that has always been with us now to this date. So please have fun and enjoy.
Absolutely. And to that end, this is a jam-packed session. There are a lot of goodies, takeaways for all of you to apply in your day-to-day, like immediately after the session. We will make the slides available to you as well as the recording of the event. Just be sure to submit, again, less than 3 minutes it takes to complete the survey. You'll be able to have early access to all of these incredible resources. So with that, Dewas, I kick it off to you. We're excited to hear from you.
Yeah, thank you so much, Ray. Thank you so much, Samantha and the team. Let me try to take control over the session and we can get started. Please let me know if you can see my screen.
Yes,
all right.
Good.
Yeah, thank you very much, team, once again. My name is S.T.A.R, and I am a senior security researcher here at Microsoft. And today I'm going to walk through the life cycle of some major threat incidents that we see in the cloud. Specifically, we'll talk about the reactor shell and briefly talk about the Shai-Hulud 2.0 campaign and what are its impact on the cloud runtime. By the end of the sessions, we will have an understanding of how these attackers move from a single point of entry or a single line of code to full control over the control plane or the cloud compromise that they can take over. All right. Let's briefly start with the scale of the landscape we are trying to defend here. Our research shows that about 644,000 domains were exposed to React to Shell RCE almost immediately upon disclosure. The CVE score for this vulnerability was 10.0, which could be the maximum CVE score that ever was. We are also seeing about 2.6 weekly NPM downloads at risk, creating a very massive surface areas for campaigns like Shai-Hulud 2.0. Critically, about 67% of these breaches are now linked directly to identity harvesting, which explains like about why about 90% of the organizations we have are reporting container security incidents towards their SOC team. When it comes to containers in the cloud, root access no longer is the ultimate prize that the attackers are trying to get into. They are trying to get into the identities that these containers have. Container might be ephemeral and it might disappear in minutes, but a harvested cloud token that we have can outlive the cluster, which allows the attackers to bypass the entire perimeter. The attackers aren't just trying to break and take into your applications. They are trying to utilize the application in such a way that they could expand. Like the Shai-Hulud 2.0 campaign here proves that a single poison hook that you could implement moves into a machine speed layer through your CI/CD pipelines, turning your own build pipelines against you. We also we'll be briefly talking in the upcoming slides about the modern RCE and how they are very silent, which if the attacker operates entirely in this case the attackers operates entirely in memory without ever forking a shell or touching the disks. Basically what the EDR is actually looking for, it does not give those signals, so it is totally blind towards the providing the signals to the EDR. If you would look at the diagram which is on the right hand side, you can see that the progression, it starts with basically web application exploits like React to Shell. From there, the runtime is being hijacked, and often under a very legitimate process like next hyphen server to gain the shell access. The final most dangerous steps is basically the lateral movement, which the attackers use via IMDS discovery and to harvest the cloud identity tokens and to achieve the complete takeover. The research that we put forward for in this session basically tries to demonstrate the attackers have moved beyond the simple execution into the containers. They are now achieving the interactive cloud integrated access to aggressively harvest the secrets, to dismantle the local security controls, and then to monetize their presence through the persistence backdoors or moving forward to crypto mining. Let's deep dive into the first threat campaign that I talked about from the attackers, the React to Shell exploit. The React to Shell exploit tries to leverage the insecure deserializations, which is there in the React server components, which we call it as the RSC, in place to achieve an unauthenticated arbitrary code execution at the application layer. So if you would ask me, the exposure of this application is remarkably very simple. By default, merely adding just the next action header will trigger the internal parser, which in place would require no prior authentications from the attacker. That means there is no authentication in place. Technically, if we when we move technically deep inside this particular activity, how it is being carried, the exploit utilizes the gadget construction chains. This chain links the internal references back to the function constructor, enabling the execution of arbitrary command directly within the runtime environment. If we would look at the flow at the bottom side of the slide, it begins with a very crafted HTTP post request, which targets the React server components or the next.js endpoint. The server then tries to deserialize the attacker control flight payload, which leads immediately to the arbitrary code execution under the node.js runtime. Once this code execution is achieved, the attacker then moves quickly to harvest the high value assets like the AWS keys or the .environment files or the NPM tokens which are available in the containers. While parallelly doing this, the threat actors also try to deploy the C2 implants or the custom remote access Trojans at this stage. The end objective basically of this threat activities are usually to typically monetize through making use of crypto mining such as Eximbric, to call the IMDS server to exfiltrate secrets so that they could take over to the cloud, or to establish data exfiltration channels to an attacker controlled C2 server. Moving on to the next slide. During this particular process, we also have seen something very interesting, interesting activity which I wanted to highlight. In the current days, a very highly advanced persistence methods in this campaign involved an in-memory manipulation of the node.js runtime. When you ask me what the in-memory manipulation is, basically the attackers use the process of monkey patching. So monkey patching refers to the practice of dynamically modifying or extending the behavior of the existing code at runtime. So by monkey patching the application servers, the attackers embed a resident backdoor that avoids the file system entirely. So what happens is the payload hijacks the http.server.prototype emit that we see here, which allow it to intercept with the raw HTTP traffic before it even reaches the next .js routing layer. What happens then? This in turns creates a hidden path, a web shell, which triggering only on very specific signatures, like the one which is highlighted here. You could see when a URL like robots.txt is being passed to the when it is being passed, while allowing all other traffic to flow undisturbed in the environment. This particular selective execution makes the backdoor exceptionally difficult to identify through traditional logging or any kind of auditing method that we could have. Also, there were some very interesting activities that we see. While a lot of RCEs that we see spuns up a lot of shell, we have shell-based exploits which are very common. In this particular scenario, we've identified that a more discrete category of node native threads, what we call it as node native threads, unlikely any kind of typical reverse shells that basically relies on spawning external libraries such as bin/sh or curl. These payloads operate exclusively within the memory of the existing node.js process. By remaining in process, the attacker avoids triggering the runtime security alerts that monitor for anomalous child process creation. This example, like the example here, illustrates that how they leverage the internal modules to harvest data while remaining attached solely to the Node.js loop without leaving any traces for the process tree. So there are the log-based thread detections or capabilities that we have remains unnoticed from those triggers. The React to shell lifecycle is being characterized by a rapid transitions from how we start at the beginning, like the unauthenticated RCE, to a very multi-staged industrialization of the breach, which covers a lot of parallel areas like identity thefts or the persistence into the environment or the monetization, making use of those containers which are deployed in the cluster. In this particular slide, what we are trying to do is now we're trying to move from the how of the exploit to the how of the operations. Once the exploit happens, once they are inside the container, what are the different activities that they could do? The what particularly makes this campaign very dangerous is the speed of this transition. And an unauthenticated RC doesn't just sit idle. It immediately pivots into different parallel work streams. The first work stream that you can see here is the identity harvest. It is usually the first priority when a threat actor enters into the environment. The attackers try to utilize this DNS-based validations through tools like OST5 to confirm that the breach that they have done is live. And they could be rest assured that they are able to maintain their presence inside the container. Once they validate this, they immediately begin the probing of the IMDS servers and try to dump the environment variables to scavenge through the high value cloud credentials before exfiltrating them to their C2 servers, which are using the outbound HTTP post requests. They, in pillar number 2, they also simultaneously they try to establish some interactive access. This involves creating of reverse shells via the FIFO pipes and performing the hands-on keyboard targeting of the sensitive developer artifacts like we have like .ssh or .npmrc files. For persistence, we can see them fetching the sliver or ELF binary implants and setting up the systemd or the cron-based hooks to ensure that the C2 channel remains active even if the container restarts. One of the major things that we could see is the pillar number 3, where they try to monetize the existence into the cloud. This isn't just about dropping miners. It is also sophisticated. It involves a sophisticated cleanup process where they try to clean up the scripts which are there from their competitive other existing miners, trying to ensure that their own exam rig or the custom mining payloads have 100% of the CPU resources. So whatever I talk right now, I would want to create a bigger picture. Like I created this image diagram here to give an understanding of the entire attack flow within a very standard Kubernetes architecture, which is there even in AKS, EKS, or GKE. The attack begins at the external internet, where the threat actor or the supply chain worm bypasses the ingress WAF using the React to shell vector we have discussed. Once inside the containers, the attackers try to hijack the next.js application container process memory. You could see in the center part, which is been expanded over. The data flow here from the compromised memory heap, they are trying to reach out directly to the instance metadata services to harvest the cloud credentials, which is on the top right side of the diagram. They try to validate the environment by making use of the OS listeners and exfiltrate secrets to an attacker control C2. On the center left-hand side, you would see that while identity is being harvested, the attacker establishes an interactive access. So look at the flow between the pod and the external C2. They are trying to migrate to a stabilized C2 infrastructure to maintain a permanent hands-on keyboard presence. In the right bottom corner, you can see for persistence, they utilize the fileless memory resident backdoors, the one that I recently just talked about, and retrieve the binary implants like a sliver using MTLS to secure their communication with the external data exfiltration servers. They in turn also try to install persistence hooks that bypasses the container restart. So effectively what it does is effectively it lives inside the worker node rather than just the pod. So which makes them implementing their persistence even stronger. On the bottom left hand side, you could see that they also work on the monetization section. After the competitive cleanup, they try to deploy specialized installer scripts. This usually results in the what we call something that as the resource usage meets K8s scenario, where the crypto miner consumes 100% of the pod CPU, potentially trying to trigger auto scaling that only serves to increase the attacker's compute power and increases the bill of the victims in from the victim's billing as well. The one of the major reason why I wanted to explain about this the diagram here is the diagram here highlights why the network level security is insufficient. The attacker is operating inside the trusted process memory and utilizes the trusted bounded paths. One way to defend is for us is to focus mostly on the identity based egress filtering and the runtime memory protections that can spot this fileless methods. Here, these are some of the artifacts that I wanted to present from our day-to-day hunting during this activity that we find out. The the practical detection relies on identifying behavioral anomalies, while the runtime moving from the abstract attack to the raw command line signals found during active hunting. In the first part, the section 1, the discovery and the initial validations, immediately after the threat actor have an RC, the first signals are the validation props that we have. The attackers try to run the who am I commands to confirm their permissions and use recursive find operations to look for any existing environmental artifacts. They also try to immediately probe the cloud metadata layer using commands such as curl to hit any kind of S3 endpoints to verify if the container has a path to the cloud control plane. In section 2, the staging and in-process executions, you would see this is where the evasion gap that we recently discussed about becomes visible. To bypass this loud process tree monitoring, attackers usually leverage the node native execution here. So instead of spawning a new shell, they use the command such as node-e to pipe the malicious JavaScript directly into the running process's memory. We would also see that we also saw, that the deployment of the secondary staging scripts, often with high fidelity names, which we could see in the screen here, helps to pull down more complex payloads. On the bottom left hand side, you could see once the execution is stabilized, the objective shifts towards the monetization, primarily through crypto mining. And one very interesting behavior, as I talked about, is the competitive evasion using like p-kill to aggressively terminate any pre-existing miners. On the bottom right hand side, you could see the persistence and stabilization. This commands were being used by the threat actor to ensure they don't lose access. The attackers try to deploy the C2 implants using commands like colonia.i486 to create bidirectional command channels. They use no-hop on scripts like alive.sh to survive any container restarts and frequently masquerade themselves as the core system services, naming their binaries like systemd-devd to blend into the process list. I will quickly switch gear and talk about the Shai-Hulud 2.0, which is another threat camping, which is basically a supply chain attack. This isn't an exploitation of the cloud, rather it is the poisoning of the supply chain. The Shai-Hulud 2.0 supply chain attack represented as one of the most significant cloud native ecosystem compromises that we recently observed. The attackers maliciously modified hundreds of publicly available packages, trying to target developers' environment, their CI/CD pipelines, and the cloud-connected workloads to harvest any credentials and configuration secrets. Basically, the threat actor compromised multiple NPM packages by adding a set_bun.js pre-installed script to the package.json file. This script performed an environment check for the bun runtime, and if it was not able to find the bun runtime, it silently installed the binary to serve as an alternative execution engine. The bun runtime was then used to execute a bundle script called bun_environment.js. So this secondary script downloaded and deployed a GitHub Action Runner archive to establish a persistent foothold. The attacker configured a new GitHub repository and then initialized a runner against the name called as Shai-Hulud for remote orchestration of this particular attack. Then specifically making use of tools like Trufflehog, runner.listener, they were able to extract the downloaded archives which contained credentials for their credentials harvesting. I will quickly try to walk through with the life cycle of this cloud native worm, how it works. The first step is starting with the runtime shadowing. The attackers use a pre-installed script, as I talked about in the previous slide. Now, if you ask me why Bun, Bun is a modern all-in-one JavaScript runtime and toolkit which is designed for speed and simplicity. It serves as a very direct and high performance replacement for the Node.js or the Dino, aiming to streamline the development process by integrating several distinct tools into a single executable. Because this particular bun, it's pretty fast, often it gets unmonitored and allow them to bypass any kind of traditional node-centric security that we see. Now, after it gets a foothold into the environment, what it does, it follows the same process that we see in the React shell environment. The worm performs a recursive file system scraping, tries to identify any kind of secrets which are available in the environment. It hunts for the key. It looks for any kind of kubeconfig, .kubeconfig files, and the data doesn't go. What it tries to do is the data, it doesn't directly go to the C2 IP immediately. It usually push the data into a public repository by using legitimate platforms as staging grounds, and the exfiltration traffic blends into your normal developer activity. So the environment or the defense mechanism that we have set up here doesn't even have the idea of what is happening in the background. And the after that, it moves towards the infrastructure persistence. This is the most critical pivot here. The worm tries to deploy some GitHub native self-hosted runners. This try to establish a persistence bidirectional command and control channel that lives entirely within that tenant. Finally, it leverages the stolen credentials to inject backdoors into the downstream package dependencies. This is how the worm moves horizontally across the global software ecosystem. Now, I wanted to converge both the stories and try to paint a big picture here. So regardless of how an attacker enters the environment, the objective of them is to reach the IMDS endpoint. This is one of the very important critical bottleneck that is there in the cloud attack chain when a temporary web hack or a worm graduates into a permanent cloud takeover. Depending on the nature of, like, for example, what accesses the application have, they like, for example, if it has high privileges, if they are able to take, if they are laterally move into it, they could even reach to very critical resources in the cloud, like Key Vault, and exfiltrate the code and take the entire access towards the cloud environment. We spent like about last 20-30 minutes trying to talk about how an attackers operate. Now let's try to talk about how do we go ahead and then stop them. Basically, I have put down here some basic hygienes and hardenings that basically in your container environment, what we could do to make sure that we could protect ourselves as much from this kind of threat campaigns that makes use of vulnerabilities from web shells, from web applications or any kind of supply chain worms. So I have pasted down here. I will not be going too deep into this, but it basically tries to cover about like not keeping your environment exploitable, make sure that it is hardened. Any publicly accessible resources or APIs should not be publicly available to the customer, and use the mechanism of zero trust in the cloud, specifically when it comes to container, where we will be hosting applications which could be of high fidelity and have high permissions in the cloud environment. I have also pointed down some detection queries that are available for the audiences to check in their environment to see if there are any kind of potential React to shell command injections attempts. I have added it in the slide. You may want to go through over it. Similarly, I have also added the hunting queries for Sci-Hulu 2.0, where it tries to identify or detect any kind of setup of the GitHub runner within the malicious repository and try to download the malicious bun.sh script that facilitate this supply chain worm in the environment. Finally, there are some detections which are available for React to Shell in Microsoft Defender and all the categories: Defender for Cloud, Defender for Endpoint, and Defender antiviruses. You may want to go through this to see if there are any kind of such detection triggers in the environment. And same thing, we have the detections for each tactic and each steps that we have for executions behavior, for infrastructure C2, and for data impact, which are available for Sci-Hulu in the Microsoft Defender environment. Finally, these are two publicly available blog posts that we have, the Microsoft Defender for Cloud team has published, and which gives more detail about these two attacks that I talked about. Thank you very much, team. Now I will be handing it over to my colleague Avi Sharma to go forward with the additional contents.
Hi, thanks. Thanks, Devas, for this session. I think it was very insightful, and I think I'll be picking up few pointers from what you already mentioned. Let me share my screen and get started quickly. Just a second. All right. Can you see the slide? Devas, can you confirm?
Yes, I can see the slide.
Great. So first, I would like to request a few reacts coming for Devas's presentation. That was really insightful, and I'll build on top of that. A short introduction about myself. My name is Avi Sharma, and I'm a security researcher for containers, specifically in Microsoft Defender for Cloud. And today I'll be talking about supply chain attacks on AI workloads in Kubernetes. A few pointers before we start with this session. This webinar and this particular topic is aimed towards opening your mindset around what we are seeing and what we will be seeing in the coming few months and years. Hopefully, this should help you drive your security efforts in the right direction, at least in the Kubernetes and AI workloads context. If you have any questions, uh, please feel free to use the module or share them with the organizers, and I'll take them up later. So let's get started. So firstly, I wanted to talk about why supply chain attacks on AI workloads matter. Uh, Few recent stats that have come up from the CNCF Foundation state that if you are self-hosting an AI workload, most likely it is to be hosted on a Kubernetes cluster. If you're not using a SaaS platform like AI Foundry or AWS Bedrock, it is more likely to be hosted in a Kubernetes container. And while that adoption is increasing fast, we're not seeing the same detection capabilities or the existing Kubernetes containers getting the required security. So that adds to the challenge for us defenders and why this is important right now. So wanted to talk about why AI changes the threat model. Firstly, the models that are loaded are executable artifacts. When you load a AI model file, a PyTorch format file, Python automatically runs any code the attacker embedded in it. So no exploit is needed, no vulnerability is needed. The run code on load behavior is built into the file format by design. And if we talk about agents, let's say like OpenClaw, those execute autonomously. So if an attacker compromises those, he gets the access to that autonomy, which is rarely uh, audited in the current set of detections and telemetries. Often the GPU nodes, which are used to run these models, they also run overly privileged, so they have elevated kernel access. So if someone compromises those GPU nodes, that can lead to higher level access on the node itself. And the CI/CD identities that are used to push this pipeline through to the cluster, those generally have very overly permissive tokens, which can be misused if not scoped and configured correctly. So in traditional Kubernetes versus the AI native threat model that I'm proposing today. So in traditional Kubernetes, defenders ask the question, is this cluster misconfigured? In an AI workload running on Kubernetes, we must also ask, can I trust every artifact this cluster is about to execute? So the traditional Kubernetes threat model, it talks about the main threat is the misconfiguration and container escape. In the AI native threat model, the threat also includes, and keep in mind this is an additive. So the threat also includes trust chain abuse. So the attacker can poison what the cluster willingly runs, since their artifacts are code, in fact. What stays the same? The normal misconfigurations, exposure, service account, token theft, network policy gaps, they stay the same. These risks apply on top of those. And what changes completely, the detection boundary is moving to the artifact layer. Your SIEM, admission controller in the cluster, the EDR, they don't inspect these LLM model files. And the attack surface is also increasing. It's moving externally towards third-party model providers like Hugging Face or PyPy, where your model dependencies are hosted. So I took some time to extend on on some work that my colleagues had done previously. So we had built a threat matrix for Kubernetes, and I have tried to add some AI context on top of that. I won't go through this all the points right now. You can refer this slide deck later. But I just want you to keep in mind that these are building on top of the existing tactics and threats already in place. And we are going to talk about some of these techniques in the coming slides. So let's talk about the attack surface. When you're running AI on Kubernetes, if you look at this diagram, we are talking about on the left side, you have the internal attack surfaces, and towards the right, as you move towards the right, you have the external attack surfaces. So internally, we have exposure of, let's say, the cloud metadata service, the Kubernetes API, or the agent application itself. And as we move outward, we go towards, let's say, the container registry getting compromised. If it's your own container registry, it still lies within your own internal boundary. But in many cases, sometimes these registries are outside the organization scope. So they are moving externally, the boundary is shifting. And same for the model and package sources. So Hugging Face is a common platform where you can get these models. And if those are compromised, similar to what Divas mentioned in his slide about NPM packages being compromised upstream, the same impact can be seen in the future on AI workloads, which are hosted in third-party providers. What we have seen in real world telemetry. So we see a lot of clusters using the mutable image tags in machine learning namespaces. So if you have a image tag, there is slow drift over time. So if you're not pinning the container image digest in your code, and if you're just referencing the tag in your code, you're failing the validation because the attacker can change what the tag resolves to, have a different digest, and that can be malicious, and that is not being tracked. The second thing we also saw, there is a lot of runtime dependency installations happening. This is very rampant. In our telemetry, in our customer telemetry, we have seen this actively happening. So it's all the more important to keep a check on what is being installed at runtime. Are those sources approved or not? The next one we already covered. So let's say the privileged GPU, if you have GPUs being used for these models, they're often privileged, and that gives a privileged escalation path to the attacker. And we have seen this in our telemetry as well. And we have also noticed that it's routinely and fairly common to have CI/CD identities with overly permission roles. Wanted to bring your attention to some of the real world AI workload attacks. I won't talk through all of them, but I'll bring your attention to some of them. So we started in around 2024 when we had an application called Shadow Ray. It has some vulnerabilities, and if your instance was exposed, those were actively targeted by attackers back in 2024. And there has been a recent resurgence that we saw in 2026 as well. A couple months back, we saw the same vulnerability being exploited again, just a new wave across multiple clusters. So it's important to note the vulnerabilities and the exposure of the workloads that you're running on Kubernetes. That's a given. That is something that we have been doing for a long time for different application types. But what has changed since, let's say, last September in 2025, we started seeing malicious MCP servers first. So that has started the supply chain side of the attacks that we are seeing. Then there were more cases, let's say like the Keras supply chain attack, where a malicious code was hidden inside a widely used Python ML package, which was distributed by PyPy. And it was missed. It was missed by the static scanners because the payload was obfuscated. And similarly, couple in February, couple of weeks back, we also saw a benign case of OpenClaw installing Klein on all systems. Although there was no activity post this installation, the vehicle is there. It shows that this can be maliciously used in the future. So let's talk about the traditional attack sequence for AI workloads. Let's say the CVE path first. So let's say you have a Langflow instance running on AKS and it has a vulnerable RCE. From there, the attacker usually tries to pivot forward using the IMDS token, as Devas mentioned. If he gets the tokens from there, he is able to access the control plane. From there, he is able to enumerate all the services and clusters the managed identity or the cluster has access to. If that managed identity also has access to a key vault, which it often does, those keys within the key vault can be taken forward to move forward and do a full account takeover. So the impact is far-reaching. This sort of attack sequence we have seen in the past as well. But I'd like to draw your attention towards how the AI supply chain attack sequence changes this. So if we see, the steps are fairly simple after the initial access, but the dwell time has reduced dramatically. There are no CVs required, and it's almost invisible to the current detections and telemetry that we are capturing. So you start first, let's say your continuous integration or your pipeline was compromised. So your GitHub account, GitHub token was stolen. Maybe it was let out in the open in some repo. Maybe that was used as a starting point. From there, the attacker can take over and poison the artifacts within that particular repository. Once that has been done, the pipeline will continue as intended originally. It will push that image or the code to the registry, and the cluster will auto deploy it. The only change that happens is at the time of the model load, it will run that malicious payload and move forward with the IMDS call and pivot and laterally move to other services. So this is the mindset that I want you defenders to look into in your own environments. Keep your mind open to such attacks and the likelihood of such attacks happening more frequently in the future and the coming months. So let's look at one of the adversary trait graphs. So there is a deserialization that we saw in reactive shell that they was covered. Similarly, when some models from, let's say, Hugging Face are downloaded, uh, there's still around 48% of models that use these insecure pickle deserialization methods over safe tensors. So it's fairly common still, at least in the legacy systems. And most of the common models that are available, they still have remnants of these pickle deserializations still present. So what the attacker can do, they can override the reduce class of the code to put in their own commands. So in this case, they are posting a command to contact the attacker C2 and executing that on the OS using curl. And this reduce class actually loads before the model is even loaded. So let's say this is the only line of change the attacker does in the compromised GitHub repository. When this moves downstream, this command will be executed on your system, and it's highly likely that your current set of detections will not capture this even happening. There are more trade crafts that adversaries are using. I'm just highlighting a few. Maybe take time to delve deeper into these topics. So the first one we try to cover, so malicious pickle payload injection. The second talks about the low rank adapters backdooring. These are small files that are used on top of base models, let's say bigger models, 70 billion parameter one. So these are generally very small in size, and these fine tune the context of that model to your use case. And because of that, these are commonly available and shared within teams and on third-party communities. But the problem is these adapters can be backdoored, leading to the whole model being compromised. Another common occurrence that we see is dependency confusion. So attackers can try to name packages, your internal Python packages, and register them in online repositories with the same name. So when the pip tries to install that particular package, it refers to the online repository and downloads the malicious one. And this can we can also have a variant to this case where there is typo squatting possible for the package names. The next few talk about the registries where the Helm values in the Helm charts can be modified if the attacker has access to the CI pipeline. We already discussed the case about the image digest swap where the tag is unchanged, but the underlying digest has been changed because the image has changed. Uh, and there are a few more methods. Let's say if you modify the Kubernetes manifest itself, if you change the spec and you inject a new sidecar container, uh, uh, what is the likelihood of that being surfaced in your detections, or will you even be alerted if a new sidecar is injected? The last one is agent skill marketplace poisoning, and this is fairly common, fairly recent, which we saw in some Claude bot attacks of late. Um I think from last month itself, we have seen around 100 plus malicious skills being uploaded on the marketplace. So when these agents pull those skills downstream, they can take that poisoned code and infiltrate uh, into your environment. So all these are worth keeping in mind. Maybe try to think about these tradecraft points in your environment as well. Try to look for them and have some detections ready for them. I'd like to again refer back to Devas's point about the identity risk, where the regardless of it being React to Shell or Shai Hulud, it's moving towards the identity at one point. And I'd like to surface another interesting point here. So in a compromised pod, on the surface, we just see that the pod is compromised, the attacker has shell level access. What else can he do, right? He can make the IMDS call. But all these AI pods, they also have in-cluster identities. If these are federated, that also adds additional risk. There are often CI/CD identities and tokens also configured within these clusters, which can be misused. And also the agent identities themselves can be misused, which are more likely to have overly permissive permissions configured just for the agent to do its normal functioning. So whenever you look at a pod, try to look at the identity side of it very clearly. Do keep in mind that there are different types of identities within the same pod, and there is a impact that can be derived from all of them. At Microsoft, we try to think of different ways the attackers can get in. We do this via red teaming ourselves as well. And one of the insights from that is the attacker decision tree. How are the attackers thinking of exploiting Kubernetes or gaining access? So we have the general path of a CV being there and you're getting an unauthenticated RC. That's fine. That's clear. But now we are also seeing attackers moving towards the supply chain, maybe a malicious package being dropped upstream, and that is on the agent pod start. It initiates that code, and that's how the attacker gets access. Another way is by the malicious skills that I just talked about. Those are now being used to uh, push the attacker's agenda forward. So basically, what I'm trying to convey is there is a clear thought process to the attacker mindset. If they get stuck on any one of these paths, they're going to move to the next one, next one, next one, and try again and again. So you also have to think in the with the same mindset. What are the pivot points? What are the decision points that the attacker can take in your existing environments? I'd like to also highlight some current detection gaps and blind spots. On the left side, you see the points where the tooling fails and what you can do to detect them. So in case of pickle deserialization, if there is no visibility, what you can do is you can look for in the cloud process events telemetry, you can look for Python or Torch execution followed by a IMDS call within 60 seconds. Generally, these inference pods don't need to call IMDS, so it's worth taking a look at. Then if we talk about runtime pip installs, they blend in, they're very noisy, they're expected as well, but try to form some form of drip detection with a baseline and see if any new packages show up, at least in your production namespaces. GPU nodes are generally outside of EDR coverage because of the compute that is required by the EDR. But in Defender for containers, you can get that telemetry because of the eBPF sensor in the agent. Registry tag mutation is generally silent. There's no alert on this. So you should also try to formulate a way to check for hash drift. So you can capture the image digest hash at deploy time. And when the pod is starting, just ask it to validate if the hash is same from what is expected. A small change in this code, a few lines of code can really help you uh, mitigate this issue. The last one is about agent tool calls being untracked. So we are seeing agentic solutions coming up on Kubernetes. It's very important to detect their agent sprawl, what sort of identities and resources they're creating, and at the same time, uh, uh, maybe use solutions like Entra Agent ID, with which you can monitor the activities of these agent tool calls over time. If you don't have access to that, maybe try to form your own baseline, come up with nomenclatures to standardize agent identities in your environment, and try to then build detections for those segregated set of identities. I have some hunting queries. In interest of time, I won't go through all of them. I will, however, drop them in a GitHub repo with comments. If you have any questions, you can raise a GitHub issue for it. But basically, there are a few interesting points where you can start your hunts in your environment. So let's say kubectl execution inside an AI pod, especially an agentic workload, it's not really required. So you can track this. You can track for the IMDS calls coming from these inference pods. You can look for this specific CV about LangChain with this query. And this is basically to track the drift between the packages being installed by pip. So we have a baseline set around 72 hours before, and then you can validate it against another baseline snapshot taken a day ago. So this can help you form a baseline, at least give you a starting point of what you should be looking at. The next one is I have another set, and this the first one basically talks about the IMDS token harvest if it is successful, and if we are seeing another Azure CLI call just after that IMDS token harvest, we can track that. Sidecar injection, if a new sidecar uh, has been created within the same pod, that can be detected with this query. And we have a couple more for few specific attacks and some dependency drifts, which you can go over later. One point that I would like to highlight from a governance standpoint is there's no clear-cut way in Kubernetes to filter for AI-only workloads. If you look at this line here, I'm looking at a few commonly used terms to look for AI workloads, but this is not an exhaustive list. There are some strategies that you can use. One, you can also look at common image names, keep that that array available to you when you're doing your hunt. You can also leverage Defender's Cloud Security Explorer. It has some pre-built queries to find out which of your Kubernetes clusters are running AI workloads. You can leverage those pre-built queries within Defender to figure out those clusters and then hunt on top of them. So it's important to keep in mind, make your own list, maybe share it with the team. I will share my array list in the GitHub repo. Okay, so there's an interesting hunt evidence that I found in our telemetry. This is anonymized, but the things to track on this slide are firstly the time. So at time 0, we saw in a Triton inference pod, we saw pip install for Hugging Face Hub happening. So this was installed at T0. At around T1.26, so 1.5 minutes, we see an IMDS call originating from this particular pod. And that means the token is harvested generally after 86 minutes after the first pip install. And this shouldn't be happening in the first place, but let's see what happens next. After 3 minutes, we see the same pod calling Azure CLI to create a new service principal, and the name was something like a backup service principal with the role contributor. So it's basically a backdoor SPN the attacker is maintaining for persistence and later use. And this can very easily uh, you know, dissolve, and you will probably never find it in the telemetry if you don't know, or if you're not trying to look for it actively. This will just drown out in the usual IMDS and usual installation calls. But this is what we saw. This could be happening. We didn't see this was a single event. We didn't see a bigger campaign originating from this. But it's important to keep in mind that these things are happening. What you could have done to stop this, you could have blocked the IMDS endpoint from this particular pod, especially from the inference pod. If it's not required, just block it. If the attacker came in through upstream through this package, we should have kept a list of approved packages to install for the AI models to use. Maybe keep your own local repository. And the last one as well. So this command actually needs the managed identity on the cluster to have user access administrator permission or the owner permission. But we are seeing that it's commonly the case that people create these AI clusters as some form of development or research. And for that case, they assign it owner permissions or overly permissive permissions, and those are never rotated after actual deployment. Those stay the same. So it's very important for these sort of workloads. You keep a check on what identities have been provisioned, what are the permissions, and what is the scoping for those permissions. Hardening checklist. This is something that you can do as an exercise in your own organization. So we start with the P zeros. So do this week. If you are running AI workloads or any workloads on Kubernetes, the best practice would be to pin your images to the digest and not the tag. Enforce image signing if possible. That can really help cut down on the malicious or tampered images. And validate the model hash before torch load in case of pickle deserialization. You can keep these model hashes in Key Vault and reference them in your code at runtime to just have a small 5-line code check before the model actually loads, whether the hash is matching the intended model or not. Then next, as a P1 items, you can disable service account auto mounts in inference pods. You can scope the workload managed identities to minimum. Just try to look at the Defender Cloud Security Explorer queries. Try to figure out which clusters of yours are running AI workloads. From those, check their managed identities and see what sort of access they have. You might be surprised to see what you'd find there. The last one would be to block egress to IMDS from app containers. These inference pods don't need to make these IMDS calls. If they do, we can scope it separately. But if it's not required, it's a good practice to block them on the node level directly. As the later step, you can evaluate the Defender for DevOps connector. If you are using GitHub, this can come in handy to track the packages and the pipelines, and you'll get additional security context around those as well. The drift detection around the runtime pip installs and the packages. Make this a routine habit as defenders. Try to create your own baseline, track these over time, see what you're finding. Maybe you find something interesting. And for the GPU pods, if they are not really required to have kernel level access or host path mounts, try to restrict them if possible. Okay, so there are some existing solutions available from Microsoft that can help you in separate tiers from prevention, detection, and responding. Most of you might already be aware of these. I just wanted to highlight a couple of them. So for the first one is this new block here. I think I forgot to color this slide correctly, but basically the first one talks about the security dashboard for AI. This is a new public preview offering that was released a couple of weeks ago. You can go here and see your agent sprawl, your AI inventory, and overall security posture of your AI workloads in Azure and also GCP and AWS in one single pane of glass. And another interesting thing to evaluate is the Entra workload ID and agent ID. So if you're using managed identities for uh, Kubernetes, you can try and see if workload ID makes sense for you. So these are short-lived tokens, and this can help you restrict the token theft or token exfiltration risk that is prevalent nowadays. And the last point I mentioned here is about the Entra agent ID. For all the agents that you're deploying, try to use this identity because it is tracked in one place. If you don't do this, if you don't have segregation between human identities, machine identities, and now the agent identities, the sprawl will become too much to handle for management teams and for defenders as time goes on. So these are the things that you can look at. I definitely want you to check out ai.security.microsoft.com today. Okay, so key takeaways from my talk today. So CI/CD is a new parameter for AI workloads. We need to, as defenders, we need to focus on that area. Every AI pod carries three critical domains. We talked about the service accounts, the workload identity, and the agent API keys or the agent identity itself. So look at each pod in that light from now on. The IMDS reachability question decides everything. So can your pod reach IMDS? Is that call successful? One way to check whether that call will be successful or not is to look at the sign-in events from Entra. If you see a new if you see the IMDS call happening from your pod, followed by in the Entra telemetry, if you see a new sign-in for that particular identity, that is how you find out whether that IMDS call was successful or not. So you can try and look for that in your environment. Runtime behavior is your ground truth. So we have seen that at runtime a lot of new attacks are happening, and we have found this happening routinely in our existing telemetry. Uh, so this chain already exists, and it's only a matter of time since this gets more frequently used as an attack path. Skill.md is an attack surface. So agents use skill.md, and these are not modeled, these markdowns are not yet modeled for threats bias defenders. So this is an interesting area to keep an eye out for. And lastly, your detection strategy now must span the full keychain, starting from the CI to the registry to the admission controller, runtime, and identity. If we leave one of these layers unmonitored, that is what the attackers need. Finally, I'd like to end with one GitHub repository link. Here you will find the updated Kubernetes plus AI threat metrics that I showed in the previous slide. You'll find the same hardening checklist that I shared a couple of slides ago, but that also includes in-depth remediation steps that can be leveraged. There are some CLI audit scripts that can be run in your environment to find out more information about your AI workloads. And the last is the KQL hunting query pack. So this includes the queries that I shared today in the deck, plus some few more queries that can come in handy. So you can go to this repository and have a look. If you run into any issues in running any of these, you can just raise a GitHub issue and I'll have a look at it. So yeah, that's it from my side. Over to Ray and Sam.
Awesome. Avi, do me a favor. Could you go to the next slide for me, please?
Yeah.
All right, everyone. I want to bring everyone back to the screen. First and foremost, I'd like to say thank you to both Avi and Divas for being able to give us this amazing presentation. I've learned a lot, and as we all know, cybersecurity is a team sport, so this is great information and to arm the next defender expert, right? Last but not least, from a deck survey perspective, if you would like to get this recording as well as deck as soon as possible, please take the opportunity to provide, insight into our survey. It takes about 3 minutes, give or take. Again, give you early access, but also it gives us input on where we should go next in our presentations. So with that being said, thank you so much for everyone who attended, and we really appreciate you. Happy hunting.
Thanks a lot.
Thank you, team.